So we've looked at some things associated with Lewis structures, such as bond order, and we've drawn some Lewis structures. Now we're going to think about molecules in 3 dimensions. And in 3 dimensions, we use something called valence shell electron pair repulsion to predict molecular shape. The idea behind Vesper is that when we have a molecule, we have a central atom, and there are electrons around that central atom. These valence electrons that are part of bonding are all negative, so they repel one another. So they're going to get as far apart in 3 dimensions as possible. So when we're looking at the shape, we have to look at a central atom and look at all the electron groups that are attached to it. An electron group includes both bonding and lone pairs, because they're all negative and they all repel each other. So what's going to happen is these bonded pairs and lone pairs are going to repel each other. They're going to spread as far apart as possible in 3 dimensions, and that gives us our molecular shape. And that's what this bullet is saying. Okay. So in order to annotate shapes to describe geometries, we have something called Vesper notation. This is a water molecule, and you can see we have the Lewis structure, and we're going to base the predicted shape from the Lewis structure of the molecule. In this particular case, we have the central atom O, which is represented in Vesper notation by the letter A. We have 2 hydrogens bonded to it. The hydrogens are X's. X2 means 2 terminal atoms bonded to the central atom, and E2 means there are 2 lone pairs of electrons on the central atom. So whenever we're looking at shapes, we're looking at what's going on around a central atom. Now if we happen to have a long chain of carbon atoms bonded into a molecule, we look at each carbon atom individually, and we can determine the shape around that particular carbon atom. And then the shape of the whole molecule is a result of the compilation of all those individual shapes. And we'll take a look a little bit at that at the end. So here we have BeCl2 as our example of something that's an AX2. So if I draw the Lewis structure for BeCl2, it looks like this, thus AX2. Since there's a central atom with 2 atoms bonded to it and no lone pairs of electrons, that molecule has a linear shape. So anything that looks like that is going to be linear. So if we think about CO2, carbon bonded to oxygens. Carbon dioxide is also an AX2 molecule. Central atom, 2 atoms bonded to it, no lone pairs on the carbon. So carbon dioxide is also a linear molecule. So that's how my Vesper notation works, and that's how I figure out shapes. Now when we look at something that's AX3, the example they have here is BF3, a central atom with 3 things bonded to it, no lone pairs. The shape of that is called Trigonal Planar. Even if we have a double bond, for example, formaldehyde looks like this. If I look at this central carbon, it has 3 atoms attached, X3, no lone pairs. This is an AX3 molecule. It is also trigonal planar. So if we look at the SO2 molecule, there is a lone pair of electrons on that central sulfur, which means that it's AX2E and not AX3. However, that lone pair of electrons still repels those bonded electrons. So I still get the same arrangement of electrons around the central atom, but when I look at shape, I only look at what's actually bonded to the central atom. So this structure, SO2, this says angular. You can also call it bent. The lone pair of electrons is there, the 2 oxygens there. So that's an AX2E structure, which has a bent shape based on a trigonal planar shape. Okay, then we get to the most common ones, which are AX4 and their derivatives, because that would be my octet rule. I have a central atom with 4 things attached to it, which means that that central atom is following the octet. Anything like that, for example, CH4 looks like this. Central atom, 4 things bonded to it, it's tetrahedral. There are no lone pairs. So there are also 2 shapes based off the tetrahedral shape. One of them is called Trigonal Pyramidal. Ammonia is an example of this. If I draw the Lewis structure, I have NH3, so I have my A, 3 things attached to it, X3, and then E, 1 lone pair. So when I look at how the pairs of electrons arrange themselves in 3 dimensions, they spread out to form a tetrahedral shape, but the only thing I can see are things that are bonded. So I can't really see this lone pair when I look at the molecular geometry, only when I look at where all the electron pairs are. So that's why this one is trigonal pyramidal. And then we have, I've never seen this before, quite like that, H2O, 2 lone pairs, 2 hydrogens bonded to the central atom, AX2E2. Again, typically we don't call that angular, we call that bent. So water is also a bent molecule. Now, I haven't really talked about bond angles. We'll talk about them some in class. But you'll notice the bond angle for an AX2E2 bent structure is 109.5. If I go back to my other bent structure, my trigonal planar bent structure, you'll notice the bond angle is 120. And that's because there are only 3 pairs of electrons here repelling each other, 2 bonded pairs and 1 lone pair. So they get furthest apart if they're in one plane. If I'm looking at the bent molecule water, I notice that there are 4 electron pairs repelling each other in 3 dimensions, thus giving me the 109.5 bond angle, but the bent structure because there are only 2 hydrogens attached. Now, the expanded octets also give us shapes. So if we have a central atom with 5 things bonded to it, that's called Trigonal Bipyramidal. And this is an example, PCl5, an example of a trigonal bipyramidal molecule. So you can see central atom, 1 atom above, 1 atom below, and 3 atoms in the plane, each 120 degrees apart from each other. So trigonal bipyramidal is really a combination of linear and trigonal planar. And it's called bipyramidal because they have 2 triangular pyramids base to base. So with 5 pairs around the central atom, I can also have some lone pairs. So one thing you'll have to remember about these is where do the lone pairs go? So whenever I have lone pairs on something that has 5 pairs of electrons around the central atom, so AX5, I have AX4E, AX32, AX23. So there are 5 things bonded to 5 pairs of electrons around the central atom. Some of them are bonded, some of them are not. But there are 5 pairs of electrons total. If I have lone pairs, they go in this plane, the trigonal planar part, where I have 3 things in the same plane. So this shape, with 1 lone pair of electrons in the plane, is called seesaw, because if you tip this thing sideways, it looks like a seesaw. So we have this, we have the 2 down there. You'd have 1 going like that, and 1 going like that. So there's your little seesaw. Not a very good drawing, but oh well. Then, if we have 2 lone pairs, they both go in the middle, and I get T-shape. That's pretty obvious. And then if I have 3 lone pairs, and then 2 bonded pairs on the central atom, I get linear. So those are the 3 derivatives of trigonal bipyramidal. And again, the lone pairs of electrons go in the plane that makes the trigonal part. They don't go above the plane or below the plane of the atom. They go in the plane of the atom. And finally, we have 6 things attached to the central atom, which is octahedral. So this is an octahedron shape. So you can see I have 1 atom above, 1 atom below, and 4 atoms in the plane with the central atom. And then finally, the derivatives of that, I can have 1 or 2 lone pairs. Now, unlike trigonal bipyramidal, the lone pairs go above and below the plane of the atom. So we have a square pyramid here. This is your Egyptian pyramid with a square base, and then triangular sides, and then this is called square planar for obvious reasons. So we'll talk a little bit in class about why this happens, and again, you do need to know what the bond angles are and what the shape names are. The easiest way to do that is to draw the Lewis structure, figure out what type of Vesper notation would go with that Lewis structure, and then give it the appropriate name. Give that shape the appropriate name. That is by far the easiest way to remember shapes, and so it will call for you to do some memorization.